Welcome to the deep dive. Today, we're going to be tackling something that seems like it's straight out of science fiction. Satellites that just hang in the sky, always in the same spot.
Right.
We're diving deep into the world of geostationary satellites.
Right.
And you want to know how they pull off this cosmic magic trick, right?
Yeah, it is pretty amazing.
So we're going to uncover the secrets behind their seemingly impossible stillness.
Right.
Explore why they're so vital to our tech-driven world. And even reveal some surprising downsides.
All right, sounds good. It's a fascinating illusion, isn't it?
Yeah.
We look up and we see these stationary points of light,
Right.
but they're actually hurtling through space at incredible speeds.
Wow.
It really challenges our everyday perception of motion.
Wait, if these satellites are constantly zooming around Earth, how come they don't disappear over the horizon?
That's the beauty of geostationary orbits.
Okay.
They're like a perfectly choreographed dance between a satellite and Earth. There are three key factors that make this illusion possible.
Okay.
The first is that the satellite needs to be positioned directly above Earth's equator.
Okay.
Second, it needs to be rotating in the same direction as our planet.
Got it.
And finally, its speed has to be just right so that it completes one orbit.
Okay.
In exactly the same time it takes Earth to rotate, which is about 24 hours.
So it's like they're playing a cosmic game of catch up with Earth.
Exactly.
But how did scientists figure out the exact altitude needed for this to work? Seems super specific.
You're right. It is.
Yeah.
We're talking about a distance of roughly 35,700 kilometers above Earth's surface.
Wow.
And figuring that out involves a bit of physics wizardry.
Okay.
Specifically something called Newton's law of universal gravitation.
Newton's law.
Yeah, you remember that from school?
I vaguely remember that from school.
Okay.
Can you refresh my memory on how it applies here?
Sure.
Okay.
Imagine you're spinning a ball on a string.
Okay.
The faster you spin it, the further the ball wants to fly outward, right?
Yep.
It's a similar concept with satellites.
Okay.
Gravity is pulling them in,
Right.
but their speed is trying to fling them outward.
Right.
Newton's law helps us find the perfect balance where those forces cancel each other out, and the satellite stays in orbit.
Wow.
By plugging in Earth's mass and the desired 24-hour orbital period.
Okay.
The equation spits out that magic number, 35,700 kilometers. It's like a cosmic recipe.
So we use this delicate balance of gravity and speed to place these satellites in a sort of sweet spot, high above Earth. I'm starting to see why these fixed positions are so valuable.
Yeah.
It's got to be a game changer for things like communication, right?
Absolutely.
Yeah.
Think satellite TV.
Okay.
You can thank geostationary satellites for those uninterrupted signals beaming down your favorite shows.
Right.
Because the satellite is always in the same spot in the sky.
Yeah.
You don't need to constantly adjust your dish to track it.
That makes sense. No more fiddling with the antenna.
Right.
So it's all about having that constant line of sight.
Exactly.
What other benefits does that unlock?
Well, it's not just about staying locked onto your reality TV fix.
Right.
This constant line of sight is also crucial for things like long-distance communication networks and data relay.
Right.
Plus, because of their high altitude, geostationary satellites have a wide field of view. It's like having a bird's eye view of entire continents.
Wow.
This makes them ideal for things like weather monitoring, tracking hurricanes, monitoring forest fires, and even keeping an eye on environmental changes over time.
Okay, so they give us this incredible wide-angle view of Earth.
They do.
But there's a trade-off, right? I'm guessing those images aren't as crisp and detailed as the ones we see from satellites that orbit closer to Earth.
You're exactly right.
Yeah.
While geostationary satellites excel at wide coverage, they do sacrifice some image resolution.
Yeah.
Think about it like this. That delay you experience every time you have a video call with someone far away.
Right.
That's the trade-off. It's a fundamental challenge for applications requiring instant communication.
So are there other types of orbits that can get us those super detailed images?
Yeah.
What's the secret?
To get those super sharp images, we need satellites that fly much closer to Earth.
Okay.
That's where polar orbiting satellites come in.
Right.
They circle the Earth from pole to pole at much lower altitudes.
Okay.
Sometimes as low as 189 kilometers above the surface.
Well, that's a lot closer.
It is.
Yeah.
And because they're so much closer, they can capture much finer details.
Okay.
Making them essential for things like mapping and reconnaissance.
Right.
Now imagine a satellite whipping around the Earth at that altitude.
Okay.
It would have to zip around incredibly fast.
Right.
Completing an orbit in about an hour and a half.
Wow.
Clearly, that won't keep it fixed in the sky like our geostationary friends.
That's a great point. The further out you are, the slower you need to go to stay in sync with Earth's rotation.
Exactly.
It's like a cosmic balancing act.
It is.
So we've got these high-flying geostationary satellites for wide coverage.
Right.
And then these lower, faster polar orbiters for detail. Sounds like each type of orbit has its own strengths and weaknesses.
That's a great way to put it.
Yeah.
Choosing the right type of orbit all comes down to the specific task you want the satellite to perform.
Right.
So it is quite a balancing act, and it goes beyond just altitude and speed. There's a whole other layer of complexity when you think about how many of these geostationary satellites are up there.
Oh, that's right. It's not like there's just one lone satellite hanging out above the equator.
Right.
Are they all clustered together, or is there some kind of system for spacing them out?
It's more like a cosmic highway with designated lanes for different satellites.
Okay.
They all occupy that same geostationary ring above the equator,
Oh.
but they're carefully spaced out to avoid interfering with each other's signals.
Right.
Think of it like assigning different radio frequencies to prevent stations from overlapping.
Ah, so it's like a cosmic traffic management system for satellites.
Exactly.
I bet that involves a lot of international cooperation.
Yeah.
You can't just have countries launching satellites willy-nilly and clogging up the geostationary highway.
You're absolutely right. There are international organizations that coordinate the allocation of these orbital slots and frequency bands.
Wow.
It's all about ensuring fair access to this valuable resource and preventing conflicts in space. It's amazing how something as seemingly remote as space requires such intricate global cooperation.
It really highlights how interconnected everything is, even up there in orbit.
Yeah.
Speaking of the future, I'm curious about how emerging technologies might impact geostationary satellites.
Okay.
Could advancements in miniaturization lead to smaller, more efficient satellites in geostationary orbit?
That's a very real possibility. As technology progresses, we're seeing a trend towards smaller and more capable satellites.
Right.
Imagine packing more power and functionality into a smaller package.
Yeah.
This could lead to significant reductions in launch costs and potentially even open up new applications for these types of orbits.
That's an exciting thought. It's like the trend we see with computers and smartphones, more power in a smaller footprint. What about other innovations like laser communication systems?
Right.
Could those offer a solution to the signal delay issues we talked about earlier?
Laser communication is a very promising area of research in the satellite world.
Okay.
By using lasers instead of radio waves, we could potentially achieve blazing fast data transmission rates with significantly reduced latency. Imagine near instantaneous communication with satellites.
Yeah.
This could revolutionize everything from satellite internet to deep space communication.
So we might be looking at a future where geostationary satellites provide near instantaneous global connectivity.
Potentially.
That's a pretty remarkable thought, but let's come back down to Earth for a moment.
Okay.
We touched on the challenges faced by regions at higher latitudes, where the signals from geostationary satellites get weaker.
Yeah.
Are there any efforts underway to address this issue?
There are a few interesting approaches being explored.
Okay.
One involves using constellations of satellites in highly elliptical orbits.
Okay.
These orbits are designed to spend more time over polar regions,
Right.
providing better coverage for those areas. Another possibility is the development of more sensitive ground stations that can effectively receive weaker signals from lower angles.
Right.
It's like giving those higher latitude regions a better ear to listen to those distant satellite signals.
So it's a combination of optimizing satellite orbits and improving ground-based infrastructure.
Exactly.
It seems like there's a lot of innovation happening in the world of satellite communication, driven by the need to connect everyone and everything. But with all this talk about launching more and more satellites, I have to ask about the potential environmental impact.
Okay.
Is space debris a concern, especially in geostationary orbit?
You've hit on a very important point.
Yeah.
Space debris is a growing concern, and geostationary orbit is no exception.
Okay.
As more satellites are launched and eventually decommissioned, the risk of collisions increases.
Right.
Think about it.
Okay.
Even a small piece of debris traveling at orbital speeds can cause significant damage.
Wow.
And in the worst-case scenario, these collisions can create a cascade effect, generating even more debris and potentially making this valuable orbital region unusable.
That sounds pretty catastrophic.
Yeah, it's a serious concern.
What steps are being taken to mitigate this risk? Are we just leaving all this junk up there to potentially cause havoc?
Definitely not.
Okay.
Thankfully, there are a lot of smart people working on solutions to the space debris problem.
Okay.
Space agencies and organizations around the world are actively developing debris mitigation guidelines and technologies. These include things like end-of-life disposal plans for satellites,
Right.
deorbiting systems that safely guide them back to Earth,
Okay.
and even some pretty futuristic ideas like active debris removal missions.
Wow.
It's like having a cosmic cleanup crew.
So it's a combination of responsible practices and cutting-edge technology.
Exactly.
That's reassuring to hear. It seems like the future of geostationary satellites hinges on finding that delicate balance between maximizing their potential while minimizing the risks.
Precisely as our reliance on these satellites continues to grow,
Right.
we need to prioritize sustainability
Right.
and be responsible stewards of this crucial space environment.
Yeah.
It's like we're learning to be good neighbors even in orbit.
Well said. As we wrap up part 2 of our deep dive, I want to encourage you to think about the bigger picture here. Geostationary satellites are more than just technological marvels.
Right.
They're powerful tools that shape our world in profound ways, from connecting us across vast distances to providing crucial data about our planet. So before we move on, take a moment to reflect on what we've explored so far.
What questions are swirling in your head? What excites you about the future of this technology? And what concerns do you have?
Yeah.
These are important questions to contemplate as we move further into the 21st century.
It's incredible to think about how these invisible satellites so high above us have become such a fundamental part of our lives. You know, it makes you realize just how much we rely on space technology these days.
Absolutely. And that reliance is only going to grow. We've talked about the scientific and technological aspects, but there's a whole other dimension to consider: the economics of geostationary satellites. They're not just orbiting machines, they're also big business.
That's right. I remember when my family first got satellite TV, it felt like magic. You know, all these channels beamed down from space.
Yeah,
But I also remember the frustration of those delayed video calls with relatives overseas.
right.
You know, it's easy to forget that there's a whole industry built around this technology.
Exactly. The satellite industry is a multi-billion-dollar market,
Yeah.
encompassing everything from manufacturing and launching satellites to providing a vast array of services: telecommunications, broadcasting, Earth observation, you name it.
So it's this huge interconnected web of companies and services all revolving around these objects in space. And as we demand more data, faster connectivity, and more sophisticated applications, this industry is only going to grow, right?
Precisely, we're already seeing a surge in investment in new satellite constellations and technologies.
Yeah.
It's being driven by several factors. The insatiable demand for global broadband internet access, the rise of the Internet of Things with billions of devices connecting to the internet, and an increasing need for high-resolution Earth imagery for everything from environmental monitoring to urban planning.
It's mind-boggling when you think about it, all this activity happening in the silent vacuum of space, yet having such a tangible impact on our lives down here on Earth. But this also brings up some important questions about accessibility and equity.
Absolutely. As we delve deeper into this space-based future, it's crucial to ensure that the benefits of satellite technology are distributed equitably. Everyone, regardless of their location or economic status, should have access to essential services like communication and information. The last thing we want is a digital divide, where only certain parts of the world benefit from these advancements.
So it's not just about the technology itself, but also about how we use it and who has access to it. It's about creating a future where geostationary satellites help bridge gaps rather than widen them.
You've hit the nail on the head. It's about harnessing this incredible technology to foster greater connectivity and opportunity for all.
That's a powerful thought as we wrap up our deep dive. I want to take a moment to appreciate the wonder of it all. I mean, we've been talking about equations and orbits and economics, but there's something truly awe-inspiring about these machines silently orbiting our planet.
I agree. They represent a triumph of human ingenuity and our enduring fascination with pushing the boundaries of what's possible.
It's amazing to think about these invisible sentinels constantly watching over us, connecting us, and expanding our understanding of our place in the cosmos.
I feel like they're reminding us that we're all part of something much larger than ourselves.
So the next time you look up at the night sky, remember those silent guardians up there tirelessly orbiting our planet? And remember, the future of geostationary satellites is still being written. It's up to us to ensure that it's a future where this incredible technology benefits all of humanity.
Well said. Keep questioning, keep exploring, and keep looking up.
That's a wrap on our deep dive into the world of geostationary satellites. We hope you enjoyed the journey.